So hi, I'm Gideon here to show you how this game kind of works. So blockchain is a game. It's not like an actual service. It's literally a game. You play with other players. Um, it's literally just a game. This is also just a game. Here's the rules. There are piles of coins. A steal can be performed on any pile of coins, and a steal transfers coins from a target's pile to a thief's pile. And you naively trust whoever owns coins. And obviously you trust people more if they own more coins. So you trust the people that own the most. Why do you trust them? Well, because they were able to acquire the most. Therefore, you can kind of trust that they're able to acquire the most. Therefore, you trust that. Somehow they acquired the most. Yeah. So they care that much more than someone else who doesn't. Stupid, but let's hear me out on this. So what are the behaviors of players in this game? You perform as many steal operations as possible. So I play infinity steal and steal infinity times. But I trigger Omega 1 steal to counter your infinity steal. And that's a horrible math joke. Every steal declares that they're stealing everything, so I steal all your stuff. I steal all my stuff back. That doesn't really work. It's just transferring everything back and forth, so whoever owns it last has the most ownership. And a person who steals does not need to tell the network what they own, so I steal all your stuff, and then I chucked it in the ocean. Good luck stealing it back. Hashtag Titanic life. Obviously there are problems with this game. So problems is we need a stealing rate limit. Infinity steals is hard to keep track of. We need a stealing amount limit. You can't just steal everything in one steal. And we need users to broadcast where their coins are, so they can get stolen again and keep the game moving forward. So, stealing rate limit. Infinity steals is hard to keep track of. Bitcoin uses proof of work. So let's use Bitcoin's many hashes proof of work model to limit steal rate. So how long should a steal take? A steal takes a constant amount of time. What's the constant time? So, X hours. We've defined a task that takes X hours to complete. You must perform it before or as you steal. This limits steals to a rate of 24 over X times per day. So steals now have a fixed real-world cost. So proof of work can mechanically limit steals to any rate the network wants. The downside of this is that users can purchase time from other users that would let them do the task more times to obtain more steals. So you can buy coins by buying steals. So there's now a kind of a money link into the system where you can buy more ownership or more power. Is that a problem? I don't know, but it's something you can do. So stealing amount limit. We need to figure out some type of stealing amount limit. Let's consider take all or take X. Take all doesn't work. If a steal takes all of the pile at once, then users will split up their piles into the smallest amounts possible, which will require the most steals to take. This is a defensive play with high memory overhead, as you try to keep track of these microscopic ant-sized piles of coins that have literally no meaning by themselves, but combined could be a significant portion of the network. So majority network providers can simply make more claims and hold all the coins in microscopic piles, forcing out small participants. If a steal is constant, the result is the same. So when a steal occurs, it resets the time of a pile. Take all or take X does not work. So let's consider take a function of time is how much you can steal. So when a steal occurs, it resets the time of a pile. This time must be tracked with pile size. The steal takes a constant amount from a pile as a function of time since the previous steal happened. This rate limits a pile. X coins can be stolen every hour. So piles of coins get a shelf life related to their size. So large piles of coins have a lesser penalty than many piles of coins. This incentivizes forming collectives and grouping piles to avoid penalty. So this leads to a two-pile system. It works, but there's no individuality. It's really no good. Let's consider a different one. Let's use decay. So let's take a function of time, our principal value, and our decay rate. So you take a function of all that, and that is equal to how much you can steal. So what about if a steal takes a proportional amount from the pile as a function of time? So half the pile can be stolen after a constant amount of time passes. Half of the remaining pile can be stolen after another length of time. So this is exponential decay. So with exponential decay, piles can be split or grouped to mitigate the loss of coins. Everyone can claim ownership and own a small amount of coins. To get more coins, users must steal faster than the decay rate of the pile, and users with larger coin piles must expend proportionally more effort to maintain them. And all users will hit an equilibrium coin pile size proportional to what they are willing to pay to steal them. So you can, at some point, you kind of relate to everyone throwing money into the network, and you can kind of abstract, like, $10 a month of cost going into the network will net you this much, like this many coins back out of the network for you to maintain a constant supply of. So, there's a lot of slides. Alright. Now, instead of waiting for coin pile to have in value for a steal to happen, a steal can be performed at any time for a fractional amount of coins based on continuous decay. So steals take more from older and larger piles. So the older something is, the more has decayed off of it, and the larger something is, the more decays off of it in a shorter amount of time. So, a minute passes for a pile that's huge, you can still claim a huge chunk out of it, versus, a tiny pile you wait until it's basically fizzled down to nothing, and then you can claim basically all of it at once. So as time passes without steals occurring, steals claim more coins. If coins also have a real world value, then at some point in time, stealing is considered valuable, whatever valuable means. So if it's only worth it to steal at least 10 coins at a time, the user can simply wait until steals can claim that much at a given time. If there are no 10 coin steals available, the network may have grown in size, or someone trusts the network enough to have a different opinion of coin value and will perform steals for 9 coins. If a steal requires 1,000,000 hashes to complete, 1,000,000 hashes cost 7 cents of electricity, advertisers pay 1 cent per coin, so if a steal takes more than 7 coins, then the hashing work is worth doing. Alright. So this is a broadcast network. People have to be informed of where everything is. So how do you force players to reveal where their coins are? The network refuses to recognize unknown coins. So all coins must come from a pile of coins that came from a pile of coins raised to the x. So this is quite literally what blockchain currencies were built to do. You have a chain of trust that goes all the way back to the initial starting point. And if you consider all of that data, you can track where everything has come from. So in this format, we don't really have strong memory. So it's really how far back do you need to consider in order to consider this thing trustworthy. So that's kind of a problem. So we have double spending errors. So blockchains are synchronous systems, but they only need synchronicity to present double spending errors. In our system, we always steal, we never spend. Only villains do that. So coin piles are recognized only if steals are performed on it. So I will only recognize that you own stuff if your stuff is then stolen. Which sounds really stupid, but that's how blockchains kind of work, where, if a new block is made, you have no trust on it. After several more blocks have been linked to it, then you trust whatever that thing was. So you have a very poor idea of what is happening right now, but you have a very strong idea of what happened 5 minutes ago or like 50 minutes ago, and you have a really, really good idea of what happened yesterday. So the farther back in time you look, the more trust you have of whatever happened at that point in time. Alright. So, in our current system, we have no need for a global baton pass to maintain coherency and operate as a block rate limiter. To prevent double thieving, users only have to know the last time a pile of coins was stolen from, and this data can be stored with the coin pile size. So you can take one and update the other. So here's our game. Kleptocracy. There's piles of coins. You can steal from any pile. Steals transfer coins. Steals have a fixed real-world cost, so the network thus has a fixed update cost, and a lower network steal rate makes each steal reward more coins. Okay? Coin pile ownership is only recognized after a steal occurs on that pile. Alrighty then. So, what is the behavior of players in the game? So a player will steal when the trade value of stolen coins is higher than the fixed steal cost. If it is not, the player will idle, lowering network activity, increasing the reward of a steal. I feel like I'm repeating myself here. As time passes, steals will target old and large coin piles first for their higher reward, as agents are expected to behave greedily. Players must broadcast their steals so that players can then steal from them for their ownership to be recognized. So problems, we've maybe fixed some of the main ones. If you have any grievances, they can be discussed at reddit.com/r/wastevote. How do you implement this in software? Great. So this is not a blockchain. It's asynchronous. We have a constant work data block. We aren't securing serialized data, only accumulated network state, which can be represented through parallel serialized data streams. So all coins must come from a pile of coins that came from a pile of coins. So many steals can happen without knowledge of the steals that happen at the same time, unless they steal from the same pile. So we have a double spending or thieving problem, and now have designed consensus rules to help satisfy our game rules. So the goal: produce an autonomous broadcast network. Users of the broadcast network are trusted based on the amount of work they provide to the network. Excess disrupting work is less rewarding than standard work, and the evaluation of the database is a distribution of user trust represented as users' coin supply at any given time, past or present. So 2 steals and there's only 1 pile. Is it a problem? So I argue that this network will reach an optimal ratio of attack steals against normal steals, and that the consistent presence of attacks are beneficial for trusted network state evaluation. Just assume that at all time, every user is trying to perform the greediest and most disruptive move possible. This assumption will guide our baseline network rate. Preventing double spending. As you can see, this is a little bit... I'm only 10 minutes in. I guess it's not taking that much time after all. So, steal attributes. Steals need to carry a lot of data with them. Here's something that looks kind of like a programming struct. Security, current time, owner, steal amount, a target. The target is a steal. And then the target has to be updated along with this new steal associated with it. So what does an attacking steal look like? So nearly identical blocks are forged, and time is represented by decay %. So we have Alice, Bob, and Clyde. They have all produced blocks. Which one of these blocks is correct? Well, first off, you don't know when in time each one of these blocks originated. Clyde's block may have been produced first. Alice's block may have been produced first. Bob's block might have been produced first. You don't know. Clyde's block might have been made, and then Alice made her block preempting Clyde and putting in a false time. Alice could have made her block, and then Clyde could have produced a block at the exact same time, but he put in a higher time instead. So on his block, he put in a higher timestamp. It's like, oh, when was this mail mailed? It was mailed from the future. There's really no way to detect that other than by throwing a sanity check at it and be like, that's not true. But then nothing else comes to misrepresent whatever was made from the future. So then technically it's correct because there's no reason to consider it incorrect. As time eventually catches up to these false statements. So which is correct, you don't really know. So don't worry, it doesn't matter. So work has been completed, verifiable blocks made, the blocks should be broadcast. The network refuses to recognize unknown coins. So all coins must come from a pile of coins that came from a pile of coins that came from a pile of coins that came from a pile of coins until they're known. The network recognizes known coins. Reinterpreted, the preferred block should be accepted is the one most likely to have steals happen to it first, or that have already been stolen from. So if we go back up here, if we went to time 70, which one of these blocks would we target for ourselves in order to steal? So we could target Clyde's block, but the reward would be less than if we targeted Alice's block. So in this format, the block you trust is Alice's block. Alright. That's a lot of words, man. Alright. So in hindsight, we got reinterpreted. The preferred block should be the one that should be accepted as the one most likely to have steals happen to it first, or that has already been stolen from. In hindsight, we know which is correct. For foresight, we just kind of guess until what we're looking at is in hindsight, and then it's correct. Don't worry, it works. So greed is good. Don't think about what should be trusted or what's correct. Think about what you think other people are most likely to do and trust that. Don't trust history, trust incentivized future actions. So think of this more of like a chess game where you don't trust whatever the player is considering, you trust what they're doing, and you trust what the best move they have is. So, if the queen is available to be taken, chances are they're going to take it because it's probably going to be a good move. So in this, assume everyone is the most greedy agent, and what would their behavior be? So use this expectation to predict the near future state of the network and predict which block is going to have security put into it first, and trust that one until you shouldn't. So if an agent is not behaving greedily, then you should outperform their efforts by being greedy. There's no reason to not be as greedy as possible. So in this example, a person could produce a block and then link it to Clyde's block, but they're not behaving greedily if they do that. So do you really trust that block? Well, you should, because it was made. For some reason, they did that move instead of a better move of linking it to Alice's block. For whatever reason. Maybe they didn't have Alice's block broadcast yet. Maybe they didn't receive it. Maybe there was some error in the network broadcasting. Who knows? Maybe it wasn't produced yet. Maybe it was withheld from them. Who knows what's been going on? But you don't care. So greedy, attack-oriented behavior is the expectation. You might have a different expectation, but I expect every agent to be as greedy as possible. And let's make network rules that play into that expectation of everyone being a big pile of shit to each other. So alignment outside of the network could increase the productivity of the network by lowering double spending block production rates, but that's not our baseline rate. We assume there's going to be some ratio of blocks that are going to be considered included and some blocks that are considered not included, which could be considered attack blocks on the network or just, blocks. It doesn't really matter. They're just not included in history. So consensus rules. So each user's database of blocks are different. Because everyone's producing blocks and everyone's broadcasting things, you don't really have a good idea of what is truly correct at any given point in time. Again, history is reinforced while the current time is very unstable. So we've only produced a set of rules that track what should be considered truly correct, kind of. If multiple correct outcomes have been presented, it's up to each user to determine which correct outcome to build off of. So if users choose different outcomes, the network forks willingly by the user. So you're trying to convince all the users to roll with the same set of rules and the same set of standards so that hopefully they come to the same set of outcomes. And then they can kind of continue to work and build off of each other to produce the type of network that they're trying to join. So, consensus rules. Double spending. What you want to do, you replay the block data. You prefer blocks with fewer conflicting double spend blocks. You prefer blocks with known future security. You prefer blocks with more decay-rich transactions available right now. So, in the case of these, you would choose Alice's block because it has richer transactions available compared to Bob or Clyde's block. Okay. So double spending collisions are handled by the random nature of updates on the network. Bad blocks will eventually be rejected as new blocks refuse to claim transactions on them. Good blocks will naturally build higher security. So otherwise, we have a network fork and the block database diverges from a single steal difference. It doesn't break the network, it just makes two networks, which should, in kind of theory, be equivalent to each other, but some users might not talk to each other after that. So you could break up users, but the users should be broken up randomly. So it shouldn't really matter. They should still present representative samples of the network. So which fork is correct? So you trust the fork that contains a higher security density in modern time as presented by block timestamps. So we can have the network forks into two different networks, and then you join that. Your network seems to be producing 10% of whatever it was producing before. You might just want to drop that network and then go back to whatever the other network is. So you trust the fork that contains higher security density in modern time as presented by block timestamps. So work has been completed, verifiable blocks been made. Correctness doesn't really have a meaning. Each user's database of steals may be slightly different based on network propagation of correct blocks. In hindsight, we can know what should be considered correct. The value is in the replay of all steals to determine what was owned at a past point in time, so you know where the voting power should be allocated at that time. Alright, mining blocks. We only have blocks of data that hash correctly. We can order blocks based on timestamps, but we have no way of ordering them based on when the block was produced. So I can mine a block and broadcast it. Someone else can receive my block, then mine a block with a timestamp 1 second earlier that contains many of the same transactions, which could force my block off. So as blocks are produced at pseudo-random intervals, the attack block might be produced very quickly. So if it's done in this way, they've preempted my block at very, very low cost to themselves. If it is not produced quickly, then the attacker will target an even higher timestamp block to attack, as rewards will be greater. So the higher your timestamp, the more decay you can claim off of previous blocks with lower timestamps. So faking your timestamp is how you kind of like perform attacks. Alright, so if the earliest block is likely to be correct, why not mine an identical block slightly earlier? Do that. Everyone should do that. Expect everyone to do that, because everyone should be the greediest and most disruptive player possible. That's how the network is supposed to work. It works because you expect everyone to just be attacking each other and destroying whatever they own as often as possible. It's just kind of what you should expect. So by the nature of the rules, it should be the most likely to be accepted. The earliest block is technically correct. But is it? I don't know. Who knows? So mining blocks. You always attack. So blocks can be mined with timestamps declaring them from the future for greater reward. So more time has passed, so more reward can be claimed. If these future blocks are not attacked, there is a high incentive to mine future blocks that eventually become part of the trusted network state. So you always attack to defend against those who greedily attack. Attacking them actually makes the network more rewarding for yourself, and it's in your interest as a greedy agent to take down greedier agents. But then you could think of like, what if you mined a block and then you mined a block right afterwards, and then you like linked them up, So again, you trust the thing that has security put into it. But that's not truly secure. It's just kind of like, an expectation of security. So what if you mine a block containing the same transactions in another block? Then you mine another block that links to the first block, proving security on the first block. So this is a problem, and we need a new rule, at least to disincentivize this behavior. You can't stop it, you can just disincentivize it. So blocks can now only claim transactions in a time range, the time difference to the nearest linked block to twice that value. So if you want to link to a block that was made 5 minutes ago, you can only claim transactions from other blocks up to 10 minutes ago. So the reward for producing this block has now been significantly reduced. So you could do a security reinforced attack, but now you need to make 2 blocks, and that second block is going to have a very, very tiny reward associated with it. So you can steal, but it takes twice as much work for maybe twice as much reward. So it's just as rewarding to do that as just doing a regular attack, or disincentivizing it at least. So attack blocks. If 2 blocks are made with different timestamps but the same set of transactions, then the total value of the transactions on the block is the same. At any future point in time, you would rather reference a block made earlier. I already mentioned that. I should probably delete that slide. Worst case, network fork. In the event of a network fork, users can maintain a common network by tracking a master user and following their fork. Whatever blocks this user produces are considered trustworthy over other blocks that should be considered more trustworthy based on the standard consensus rules. So you could basically have one master user, and whatever this master user does is considered truly correct. So you just follow that user's blocks around. And you could use that to maintain a sort of stable network, which could be at least more resistant to forking. So network security, assumed security. So we can increase trust in user accounts by requiring all users to brute force their own accounts. Instead of accepting any RSA public key, we only accept specific keys. So by forcing all accounts to start with 32 leading zeros, we get some free block compression by assuming all accounts start with that many leading zeros. So we don't have to broadcast the full 256 bits of an account. We only need to broadcast 224. Because the 32 we already know, and we can just slap that in before we write out the entire account. Okay, So we can also forge an entirely new network with new users, and a new network that will only accept accounts with a different leading public key sequence. So while cracking a key for a network, you could save keys as you crack them, in memory, so that when a newer network is created that requires a different leading sequence, you can simply look up a suitable key for memory. So let's just, to defend against this, let's use a public key leading sequence that requires billions of attempts to land. So, at least 32 bits. You might assume more than that, but just a lot, okay? So you would have to save many terabytes of key pairs to have a chance to have cracked a key for a future network while cracking a key for a current network. So with this type of format, you could have a whole lot of different networks, and when a new network is made, you simply declare we're using this type of key instead of whatever the key is for all these other networks. And then, you have to go through the process of creating a new account for it, essentially by cracking it with just brute force operations. So you can kind of make it so when you make a new network, you can assume the network is kind of safe from user floods. So, say there's some type of contentious issue that pops up, and a whole lot of people have 5 minutes of caring about them, and they just make a new account and then upvote or downvote something immediately, and then they just leave forever. You don't really care about those users. Maybe you do, but maybe you don't. But this would kind of prevent that from happening. So, old users cannot reuse accounts on new networks. They'd have to join by cracking a new key pair, which could have an expected cost of several days of machine time. Users cannot easily create new accounts for every vote. So, anonymous voting kind of goes away if you require people to crack their own keys. Because, if I just mined blocks normally, I could mine 4 blocks a day. But if I use anonymous account for every single post, it's 4 days of blank machine time before I can start reaccruing value into my account. So you kind of try to at least force people off. In addition, because people can't easily make new accounts, users can selectively shadow ban other users without them immediately coming back. So their votes are no longer recognized in your personal evaluated database until they create a new unknown account and mine value into it. So say there was some really ignorant shit going on, and you just be like, well, I don't care about any of these people ever again. Let's just write them out of my own history, and then you just blank them out of your memory and don't consider what they're voting on. This does not prevent users from using their hashing power to mine blocks for other users. So if you notice that a user is votes very, very much along the things that you think are important, you could say I'm delegating my voting power to you instead. I don't pay attention to this much stuff, but the stuff you pay attention to is very much the stuff that I want to pay attention to. So here, take all my machine power and you promote these things instead. So, generic ending. Already at the end. Only took 30 minutes. So this is based off of game theory, blockchain, Reddit, voting systems. Shoutouts to John Nash, Satoshi, producers of the hundreds of fair and unfair games I've played over the years. That's about it. So in review, an asynchronous, security-backed, block-based P2P broadcasting network which incentivizes continuous cost expenditure into the network to secure possible history allocated voting power. Votes can then be used to construct a list of rankings to optimize the user search from social space for what people think matters at any given point in history, based on pure reward cost. To put it there, abstract as crypto coin. There's a lot of words there. It's tech speak. I don't know. No one talks like that. It's just fucking words. So I have suggested a set of game rules that I have led myself to believe are simple and secure enough to perform this task. So, in summary, let's repeat this. You make a block and target transactions to forward from at least 4 blocks in previous time. So you're required to link to a couple of different blocks. So because of this, you naturally form a small world network, which means that everything is very densely linked to one another, eventually. So you're rewarded by claiming decay based on the amount of time difference to the block and initial coin total in each transaction. Extra data can write on blocks to inform the network of things like topics, web links, statements, comments, sort of stuff you share on Reddit. Users can then vote on topics using their account's coin ownership as a voting power mechanism. Each user can then sum voting power according to their own bias to rank posts. But wait, there's more. What if there was a more exotic attack? What if someone really wanted to bring this thing down or prove that it didn't work? Or maybe there's some massive exception that people would throw at me and say, like, well, this fails because you can do this and it brings it all down, blah, 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 blah. Well, let's go over a couple. So what if a large group mined an entire subnetwork in advance and then went to dump their coins onto the main network? How do the consensus rules deal with that, since the coins have enough security backing to be accepted if history isn't checked far back enough to verify their source? You might ask this question. Good question. Coin totals aren't actually important. Just the relative distribution of coins across all accounts that hold coins. So you know how many coins there are on the network, because you have memory of your entire internal network. So lost or added coins are a possibility, but don't have a large impact if they happen, because these coin totals will be redistributed very quickly. You can't falsely maintain large amounts of coins. So what if a large group actively caused nothing but exotic attack blocks to try and confuse users' client-side databases and fork the network as often as possible? Okay, well, a network fork is supposed to happen when the network gets too large. If it's large enough to split from an attack, it was not at a stable size and should have been forked into two smaller networks before the attack. The expectation is that an attack large enough to cause such a disruption would be too costly to maintain for large periods of time. But what if it wasn't about cost? What if it was about sending a message? A large group or government could simply outcost every legitimate user on the network, and if this happened, there's really nothing you can do about it. It's a problem, but the expectation is that it just won't happen because it's expensive to do. Very possible. But what if a large group spoofed large amounts, or what if a group spoofed large amounts of P2P connections enough that the user client would not seek more connections? Then this middleman group only rebroadcast the blocks to users that fit their own network or voted with their own ideology. So this is unlikely. There's no solution if it happens. It's likely detectable as network traffic is going to be lower than expected. What if a government blocked P2P connections altogether? Centrally controlled internet network nodes whitelist addresses that it can be connected to. So if you try to connect to something that's not whitelisted, you just get blocked, or your connection is just refused. So this is unlikely outside of China. Inside of China, this is probably guaranteed to happen within 10 or 20 years. But if this happened, the block network not working wouldn't really be an issue at that point, would it? And then, what ifs. Many, 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 many more what ifs. Things I haven't considered. Maybe there's some type of more exotic attack that could just completely nullify this thing. Possible way of securing anything. I don't really know. But I think it's kind of interesting. Maybe this is a good way to build some type of digital democracy. Maybe not. But, yeah. The decaying DAG coin. If you want to go over a interesting block map, or what I've drawn up for this. So here's how this kind of looks from a block perspective. So we have a transaction here. That's what this yellow block is. For block map, this kind of defines where things go. Then we have our kind of like bit size stuff right here. This is all subject to change. Yeah. So in our block example, we have our big transaction at the top for whatever has been claimed. Timestamp, decay claim, some statements about the things. I'm just going to say we're reserving 4K for broadcasting network details. This doesn't really have much of a purpose, but I'm sure in the future the network's going to get fucked up in some massively fundamental way, and we're going to need that 4K reserved for fixing it, or maybe making it work again, or maybe it's just going to break completely, and there's no reason to include it at all. Let's just assume it's going to be very useful in the future. Don't move things around. Alright, so when you make a block, inside your block you have these blue cells. Each one of these blue cells links up to a previous block in history. So this blue cell links up to this block. All these other blue cells link up to other blocks I don't have listed here. So you form a network going forward that kind of reinforces the network behind itself. And then after you've made all these decay claims, listed all these transactions, forwarded them into your new block, whatever data you have left, you can make posts with. So do whatever you want, your allocated voting power, whatever statements you want to do, whatever writing data you want to put onto these blocks. And then like how the network mesh would kind of look is something like this. We have a lot of inputs going into each individual block that link up to each block going forward. So as a block is made, it links to some stuff behind it. As this block is made, it links to some stuff behind it, going forward to forever, as long as it continues to get used. So yeah, this is the idea. Anyways, that was a lot of words. If you've fallen asleep yet, good night. If you haven't, then thanks for staying awake and watching the whole thing. Yeah, interesting idea. Maybe you have something you can add to it. Well, yeah, that's what I'm working on, I guess. If you think you could do something more useful with it, go right ahead. Steal it. Share it with whoever you want. Again, links will be in the description below for all these types of resources. Maybe they'll get changed in the future. Don't expect this to be locked down as I try to revise it, make it more clear, and or maybe you have some way that you can show me that makes this completely, nullifies all of this and makes it not work. I'm not sure. But anyways, I am Gouda, and I will see you next time. See ya.